You should activate
Thank you.
your audio. Okay.
Thank you. Yeah,
Please
thank
start
you.
the game.
So I'm going to be telling you about a way of modeling spiking neurons in a discrete time system using complex value neurons, and then show you a very simple variant of spike time independent plasticity that can be used in this system. And hopefully you will find it useful or interesting. So why should you care about this? I'm going to sort of divide all AI models into 4 basic categories. So the first split is rate coded versus temporal coded models. So temporal codes, of course, are systems where information is encoded in the relative timing of neurons. Forgive me for telling you things you already know. In rate coded systems, you're looking at just the firing rate of the neurons. The other sort of split that I think is important is between discrete time and continuous time systems. So discrete time systems, of course, are things like the logistic map, which is famous, or any of your sort of modern deep learning systems are essentially discrete time systems, either feed-forward networks or recurrent neural networks, LSTMs and such. Then you got your continuous time systems, which are modeled by differential equations, and that covers things like the beautiful Lorentz system. And of course, the mathematical difference between these two is that one is sort of like an iterated function system, where time is measured on the integers. The other is a differential equation as an ODE, right, where time is measured on the reals. So exemplars from these categories include CTRNs from the continuous time rate coding camp. You've got your biophysical models falling into the continuous time temporal coding camp. At least these systems can encode time as spikes temporally. You've got discrete time rate coded models, sort of like deep learning. Everything in deep learning falls into this camp. Rate coding I put in scare quotes because you could have negative values, but the inspiration, the philosophical motivation is sort of rate coded. But what falls into this camp? So not much. This would be a system that is discrete time. So you just have an iterated function applied over and over again at discrete time steps. But then it encodes information in the relative timing of spikes. So it seems like those two are kind of can't be put together because you have updates happening at definite times, but for temporal coding, you want some sort of give for there to be relative timing. Otherwise, the relative timing is only at the resolution of the updates, which are discrete. So it seems like these can't fit together, but we're going to try and make it work. So the approach we're going to take is we are going to have discrete updates, but at each update, we're going to specify a time in between the updates where a spike happens. And additionally, we're going to allow for firing rates, so multiple spikes can happen. There are some constraints that we had to put on what kinds of spike trains can occur in any given time limit, but we'll try and make it work. So the 2 places we're going to look for inspiration for this are the biophysical models like Hodgkin-Huxley and the deep learning models, ANNs. So your biophysical models are nice because they have a biophysical interpretation. You have membrane potentials, you have ionic conductances, but mathematically they're a mess, right? Like these alpha and beta functions are crazy fractions of exponentials. I mean, it's horrible. On the other hand, they're also quite accurate. They can predict individual spike times. That's really nice. So it's scientifically useful. And we can also kind of fit biologically plausible learning rules to models like this. They're quite expensive computationally to run because you have to do numerical integration, and you might have lots and lots of variables for each neuron. And of course, these are ODEs, right? Machine learning makes some different mathematical assumptions. So each dendrite is modeled by a single number. Each the dendrite arbor is modeled by a vector, and a whole network of connections is modeled by a simple weight matrix. And all of the complex nonlinearity of a given neuron is encapsulated in a single pointwise nonlinearity. And this pointwise nonlinearity sort of implicitly models the firing rate of the neuron. At least that's clearly true for like the sigmoid and the ReLU neurons. Less clear for the hyperbolic tangent and leaked ReLU and things like this, but there's no notion of relative timing for activity. Activity always happens. Neurons always fire. The question is what's the value of their firing? There's no relative timing notion in here. So we can't get things like spike time independent plasticity in a machine learning model like this. But we do get some very strong mathematical tools in this system. We get linear and nonlinear transformations. So we can think about vector spaces with transformations between those vector spaces. composed of linear and then nonlinear functions. We can think of data and distributions on that data. So we get a lot of rich mathematical intuition for thinking about how these systems work, which we don't have for the sort of biophysical models. So we would like to sort of have our cake and eat it too. We would like a system that has spikes, but can also represent rates, firing rates, but also is computationally simple and sort of easy to understand in a mathematical way. So the proposal here is that we're going to replace the real valued activations of neurons with complex valued activations. And what we think that will buy us is if we interpret the magnitude of the complex number as a firing rate and the angle as a firing phase, then we can both have rate coding and temporal coding, and we can use both of those parts in different ways, and maybe hopefully biologically plausible ways. So just to clarify this connection here, I'm showing you a complex number, and for each complex number, it's sort of moving around, varying, a sinusoid, and the sinusoid is going to correspond to a unique spike train, where the maxima of the sigmoid, or sorry, of the sinusoid, correspond to individual spikes. So we can't get every single spike train in a given discrete time step, but we can get a large collection. So we both have firing rates and we have phase offsets, firing times. This is the nonlinearity that we use. If you want to know more about it, I can answer a question about it later, but suffice to say, it has a saturating nonlinearity of firing rate. So it can't have unbounded firing rate and it can't go below 0 for firing rate. But it also sort of encapsulates a trade-off between rate coding and temporal coding. So for high firing rates, you expect that individual timing of spikes is sort of less important. So the temporal coding is less effective for high firing rates. For low firing rates, you can have effective temporal coding. So this one layer tries to capture that. So we want to do an experiment, very simple, very simple experiment. Can we convert rate information, firing rate information, into firing time information and then back again? So what we did is we built an autoencoder. We fed in vectors that were encoded only in the firing rate. And then we clamped the coding layer of the autoencoder to have a fixed firing rate of 1, I think. So only information can only be encoded in the firing phase. And then you just train this as an autoencoder. You try and get the same rate coded vectors out. And if it works, then it means that information was transformed from rate coded to phase coded back to rate coded. And this does work. And there's no reason that it shouldn't work. There's a slight mathematical caveat having to do with the sort of range of input phases. But it's sort of not surprising that this should work, but it might be interesting from the perspective of, from a biological perspective, could neurons go back and forth? And there's some evidence that neurons can encode information both in firing rates and in phases. So maybe this is a way, it could be a useful way of thinking about that. So now that we have this model that can do both rate and phase coding, we'd like to try and sort of use that time in time-dependent plasticity. So that's what we're going to do next. So our complex valued learning rule has to be a function from the state of 2 complex neurons to a real valued weight update. So a complex number is sort of like 2 real numbers. So we're basically having to map from a 4D space, 4D vector space to a 1D vector space. So this is hard to visualize, and we tried. To simplify computationally, we linearize the normal spike STDP rule. So the green curve is a sort of classic rule. The purple curve is our simplified linear curve. That doesn't really matter that much, but then we just sort of scanned across all combinations of phase and rate for pre and post synaptic neurons, and we get the super ugly update plot. This is for post synaptic rate and post synaptic phase, and it's quite bad. So we decided to try to simplify it even more, and to do that, we just sort of glued together a normal Hebbian update, pre-synaptic firing times post-synaptic firing rate, and then we just added it to the this sort of purple curve for a single spike. And what we get is this much simpler weight update sort of function that captures some of the structure, but is obviously losing a lot of detail, unfortunately. So what happens in a network of these neurons, if we connect them together, if we just look at the phase distribution, so that's like the relative, that's like the timing within a bin, the firing time of each neuron. With no learning, there's no structure. So the distribution is kind of flat around the full range of firing times. when we add learning, we get the emergence spontaneously of these kind of clusters or clumps of firing times. And we sort of interpret these as phase assemblies. We don't know if that's a completely justified interpretation, but it's very tempting to do. And you see that these phase assemblies sort of spontaneously emerge and de-emerge. So this is nice because we think that this could be useful for explaining how brains actually do things, but it's happening in a very, very simple system. So this is just demonstrating that, the distribution. And you can see entropy fluctuations occurring spontaneously, where the entropy here is the entropy at each time step of the phase distribution. So low entropy means higher order or less uniformity. That means that there's more clumps or more well-defined clumps. Higher entropy means that it's less ordered or more uniform. So you can see that the network under this learning rule
Last
is
5 minutes.
okay. Well, that's all I've got actually, so that's perfect. Thank you for listening. I hope you found this interesting, and thank you to the Embodied Cognitive Science Unit for letting me do this work. If you have any questions, I'm happy to answer them.
Thank you. Yeah. So do we have any question in the chat, or you can raise your hand, or please unmute yourself and ask it. Andy.
Hi.
Yeah, please go.
Alex, can you hear me okay? Sorry, I'm on a phone. My laptop.
Yes.
Yeah.
Yes, I can hear you fine. Thank you.
So just curious. So the motivation is to find something that's discrete time, right?
Mm.
So
Yeah.
how come? So, but you know, in a sense, numerical integration is discrete time. So I'm slightly confused as to why one would want to just go with that.
Yeah, for sure. So I think that you're absolutely right. Of course, the numerical integration is discrete, but it's sort of a discrete approximation of a continuous time system. So you have to, you have this sort of knob you're tuning, right, for how small of a time step, or sorry, how big of a time step can I get away with, and have have your simulation, have your integration converge or just not explode. Whereas you don't have that knob in like a recurrent neural or like a discrete time neural network, right? There's no notion of a time step in the sense of numerical integration. So you aren't having to do this trade-off. It is computationally a discrete time, but it's trying to approximate some continuous system. So I think that the nice thing about having from the start a discrete time system is that you don't have to think or worry about whether you are simulating your system at the right frame rate, basically. So I guess it's mostly a convenience thing. I don't know if that answers your question, but
yeah, I mean, I guess that yeah, it does. It does. It's probably a longer discussion we could have about, because I guess there's also the, there's always a temporal tick of your simulation if it's in a discrete space, but maybe that's if it's in a continuous space. I'm thinking more of robot sort of. Yeah, anyway, it's probably a lot.
Yeah. I was thinking of robots for this, but I guess that's a different
Yeah. Could I, if I could follow up? So, and what overall is the motivation for machine learning or for neuroscience, would you say?
I guess it's for cheap it's for a combination of cheap neuroscience simulation and slightly more biologically motivated machine learning. It's kind of in between. It's if you have some simple problem you want to study that involves spikes, and you don't think that the details of your biophysical model matter, then you could maybe try and cook up something like this. Okay.
All right, brilliant. Sorry, I'll stop monopolizing the time. Thanks a lot. It's great.
No worries. I'll put my email in the chat if it's not available anywhere else.
Can I ask a simple question?
Yes.
So I was wondering, you said you used both Hebbian learning and STDP. Is that right?
Yeah, we use the multiplicative version of Hebbian learning. So basically the idea.
But I thought Hebbian was initially proposed, but I think STDP is also replaces Hebbian, because why this weight changes is because its information is went backwards from the postsynaptic to presynaptic one, right? So that's why the STDP came out. That's my understanding, but maybe I'm wrong. So could you explain what
I don't think your understanding is necessarily wrong. I think what I think is the case is that like the sort of classic curve. Can I go back? Yes, I can. No, I can't. The classic curve works under a certain range of firing rates.
Yeah.
And for lower firing rates, the relative spike timing really matters. But when you get into like a very high firing rate regime, then it looks more like just the product of the firing rates. And I think that this matters, like, depends on the neuron type, right? Like different regions of the brain have follow different rules. But the intuition was that it'd be nice to have sort of be able to capture both. And we didn't really talk a lot about this. I didn't talk about this at all here, but you can of course just turn off one or the other term because they're just weighted. So you can have purely the spike timing dependent plasticity, but with no dependence on firing rate, or you could have only dependence on firing rate. And I didn't like fit this to data. I just sort of put it in there to be just have two useful knobs to sort of interpolate between two different classes of behavior.
Okay.
But I think you're right that it does supersede the one. So
yeah. So I'm sorry, but we should move to the next talk. Then I can